Hello everyone, and thank you for joining. My name is Mohammad Reza Zarashahne, and today I'm going to present AGWR, Fast and Accurate Geospatial Inference via Augmented Geographic Weighted Regression. This is a joint work with Professor Oymak and Professor Magdi. Spatially varying coefficients or SVC models are popular models to use for the spatial data. These models are used to circumvent the limitations of using spatial data with global models. In these models, variable coefficients are assigned to the covariates based on the location of the data point. This helps capturing the spatial relation of the data. SVC models help understanding and gaining more insight towards the dataset, which in the end results in a better predictive performance. They have been used in many different areas such as healthcare, criminology, and transportation analysis. There are also versions of SVC models that account for different localities for different features. A common problem between SVC models is the scalability issue, as they often cannot handle any more than tens of thousands of data points in the dataset, which is a relatively small number compared to modern datasets. Another issue is the flexibility problem. Since most of SVC models are based on linear regression, they cannot capture the nonlinear relation between the neighboring data points. We introduce a multivariate SVC model called SMGW, which combined with our AGWR framework can overcome both of these problems. First, let's take a look at the AGWR framework. It is a scalable framework that combines a spatial model with a general-purpose learning model. This helps capturing both the spatial relation and the nonlinear relation between the data points in the dataset. We propose two different architectures, one of which trains the spatial model first, which is called the pipeline model, and the other trains the general-purpose learning model first, which is called the ensemble model. Now let's take a look at the pipeline architecture. It consists of three different modules. The first module is the split module, which splits the data into C different sections. Then, the second module, or the spatial module, trains a model on each of these different sections and compute the prediction value. Then, combining all these prediction values and replacing them with the dependent value, a general-purpose learner is trained on the last module over the dataset and the replaced dependent values. The ensemble architecture also contains three different modules. The first module, the split module, is the exact same module as the one existed in the pipeline architecture. It splits the data into C different sections. Then, for section I, a general-purpose learner is trained over all the points in the dataset except for the ones that are in the section I. Then, using this trained model, the prediction value for the data points that are inside the section I is computed. This helps the prediction values to be more accurate, as the general-purpose learners often tend to overfit to the training data and produce meaningless residual values. Then, in the last module, the spatial learner is trained for the section I of the dataset with the replaced dependent values. Now let's take a look at each of these modules in more detail. The first module is the split module. We've implemented different methods for the split module. The first method is the random split, where we randomly split the data into C different sections. The second one is the grid. So in this method, we grid the dataset into a number of rows and columns. These grids can share equal number of data points in them or the same dimension. The last method is the Kmeans, where we split the data into C different sections based on the C different clusters in the Kmeans algorithm. Here is an illustration of how a dataset is divided into C different sections using the grid method or the Kmeans method. Now, let's take a look at the general-purpose learner module. This module captures the non-spatial and non-linear correlation between the datasets. You can choose different methods for different datasets and purposes. For example, if you want the maximum accuracy, you might want to choose a complex model such as neural networks, or you can use a fast model such as random forest or XGBoost. And lastly, let's take a look at the spatial module. Any spatial model such as GWR or MGWR can be used as the spatial module learner. The purpose of this module is to learn the spatial relation between the data points. Now, to improve the accuracy and flexibility, we introduced the stateless multiscale geographically weighted regression, or in short SMGWR. It is a multivariate SVC model that assigns different bandwidth to different features. However, it does not use the backfitting algorithm, which enables it to remove the need to keep the history, and also it is able to build a training model using any specific given set of bandwidth. This helps it to parallelize the search for the bandwidth. Now, let's take a closer look at the SMGWR algorithm. SMGWR first initializes all the different bandwidth for different features the same and as the result of the GWR model. Then, for L iterations, at each iteration, first it generates a new set of bandwidth, and then it evaluates this new set, and based on the result, it updates the best result so far. Now, how this evaluation step goes. For T iterations, we go over the features and the observation, and each time, first we compute the weights based on the observation and the feature bandwidth, and then we solve a weighted least squares for the jth feature, assuming all the other features are constant. Then, using this, we create a model and then compute the error. Now, the first part of the SMGWR algorithm was to generate a new set of bandwidth. Since SMGWR can evaluate each set of bandwidth individually, then we can use any black box optimization algorithm to generate the new set of bandwidths. We have implemented different black box optimization algorithms into our framework. Hyperband, simulated annealing, hill climbing, Bayesian optimization, SPSA, or a hybrid combination of these algorithms are all included in our framework. This figure shows how these different methods are performing in comparison to the GWR and MGWR. GWR uses only one bandwidth for different features and is indicated with the light blue line at the top. MGWR, indicated with the dark blue line, is using backfitting algorithm and very thorough search and finds the best set of bandwidth at the cost of runtime. You can see all different implemented algorithms and their performance in the figure. To evaluate our AGWR framework and SMGWR model, we conducted a series of experiments. Our experiment setup was to use both real-world and synthetic datasets. We used the pipeline architecture and we used the random forest as our general-purpose learner. Also, due to the random nature of the bandwidth search algorithm and random forest, we averaged the result when comparing AGWR to other models. We created two different synthetic datasets, where in the first one, different features were linearly combined, but in the second one, the features were not linearly combined. Our first experiment is to compare SMGWR with two of the well-known models in the field, MGWR and GWR. As can be seen here, SMGWR is more flexible than GWR, and it also is faster than MGWR. We also used the bandwidth found by the MGWR model and passed it to the SMGWR, showing as the SMGWR star. And as can be seen in the table, it has very similar errors to the MGWR algorithm. This shows that not using backfitting algorithm does not affect the accuracy too much. This means that using a good bandwidth search algorithm, we can achieve similar error as MGWR and faster runtimes. Our next experiment is to evaluate the AGWR framework. We compare it with plain GWR and MGWR. As can be seen here, AGWR framework can achieve up to 14 times faster runtime, and also it improves the accuracy in all the different datasets. Lastly, we compare our AGWR framework with SMGWR as its spatial module with other algorithms, and AGWR outperforms other models in most of the datasets. In conclusion, we introduced the AGWR framework, a fast, flexible, and scalable framework to combine spatial and general-purpose model to capture both the spatial and nonlinear relation between the data points. Our framework shows up to 14 times faster performance than the regular spatial models such as GWR or MGWR. It also contains two different frameworks, namely the pipeline and the ensemble framework that can be chosen based on the dataset or the application. We also introduced the SMGW model, which is a stateless multivariate SMGW model. It can be combined with the state-of-the-art black box optimization techniques. And black box optimization is a very hot research topic at the moment that has many great different algorithms, and it's constantly evolving. Our SMGWR is also parallelizable. Thank you for your attention.